Alright, in this video I hope to make it quick. I'm going to try my best. What I'd like to do is look at these brain teasers that we've been working on over the last couple days, and I would like to show you the sort of hidden lesson, or the bonus lesson that comes out of it. So in the first one we had Mimi, and we found out that she was 15 based on what she said about her age relative to her dad's. And so the way I'm showing the work here, we're basically using algebra to rewrite the problem from English into the math language. So the reason I added or included this in the set of brain teasers is to demonstrate the thing that we as humans can do that computers can't. So a computer, once it gets these equations in it, can answer our question for us. But what a computer cannot do is look at these words and actually answer the question yet. But what we have now is the ability to write a system of equations that will enable us to no longer think about Mimi and Dad and their ages, but simply just follow the rules of mathematics. So as we recall here, what we have is 2 of Mimi's age 5 years from now will be the same age as Dad's age 5 years from now. So you can see how in English it makes sense, but now that it's in math, I can just do the math. Over here, if we take Mimi's age 5 years ago, it was 3 times Mimi's age 5 years ago, you get Dad's age 5 years ago. And again, just do the algebra that we should have learned last year, and whether we did or not, it's okay, we'll learn it. And we can answer the question. Mimi's 15 and Dad was 35. So just to make sure that the answer is correct, though, since I didn't use a computer, I verify that if Mimi was 15, she'll be 20 and her dad will be 40. It's twice as young or whatever. And here we're at 10, 30. So Dad's 3 times as old as Mimi 5 years ago. So it all works. Alright, the next problem had to do with lockers. Now most students did a really nice job of figuring out a way to understand this problem without having to go with 1,000 different lockers. If you start with just 10 lockers and 10 students, you can actually make a system or develop a format where you can figure out that by the 10th student, the 1st, the 4th, and the 9th lockers remain open, and all the rest of the lockers will remain closed. Now, what you do from there, how you extend this pattern, depends on the sort of observations that you make. So the first lesson that we want to learn in this particular problem is sometimes when you're trying to solve a complicated problem, it might be easier to start with something simple and then extend it to more complicated scenarios so that you can at least manage the problem. At issue is, can we recognize a pattern 1, 4, and 9? It's possible that we can just say in the first 10 there were 3 open lockers, so in 100 there would be 30 open lockers, and so on, but that's a weak theory. What I also notice here, though, is that 1, 4, and 9 are what we call perfect squares. 3 times 3, 2 times 2, and so on. So we may have a theory, but now we have to test it. It seems like all perfect squares numbered lockers would be the ones that are open. If you thought about it, locker number 15. Student number 1, 3, 5, and 15. Those are the 4 students that will interact with the locker. It's an even number of students, so 2 of them will open the locker and 2 of them will close. Any composite number that is not a perfect square will always have an even number of factors, so we'll always end with a closed locker. On the other hand, perfect squares will have factors that are odd in number, because right here we have 4 times 4. So that 4 only counts once, which means there's only 5 students in this case that could be opening the lockers, and therefore we're always going to end on a positive. So the reason I'm bringing this up is to talk about mathematical thinking and understand that just because you have an answer doesn't mean you're done with the problem. So in this situation, you may have a theory about perfect squares, but that doesn't mean that that's the answer. You have to either continue this and go to 20 lockers or 30 lockers to verify your theory, or better yet, come up with a better argument, and that argument will be able to hold weight. Alright, moving on. We've got this pigs and chickens problem. Just as before, I wanted to emphasize that we're turning English language into math language to solve this problem. Most of you, what you did was you wrote equations and used substitution to solve a system of equations and get the answer for 30 pigs and 30 chickens. And it's a perfectly acceptable method, and that's algebra. That's what we're here to learn. But I wanted to demonstrate that there's another tool available to all of us, and that is just the ability to understand the problem on a case-by-case basis. So for example, here I can say I just need 70 heads, which is 70 animals. So if I can do that with 60 chickens and 10 pigs, that would make 70 heads. However, we would see that there's only 160 legs between them, so that's not right. And I can just keep kind of making educated guesses until I move towards 200 legs. You can see here as I added 5 more pigs, it increased the number of legs to 170, so I should continue in that direction. Eventually we can complete the table and discover the correct solution without even having to do any algebra at all. Now, of course, again, we're here to learn the algebra. This is the stuff that we want to learn how to do. But we also, as I mentioned before in the locker problem, need to find a way to verify that our answer is actually reasonable. So if we look at a problem from dual perspectives, here's a table to answer the question, and here is an algebra to answer the question, or here's a graph that answers the exact same question. Now understand that this is the equation P plus C equals 70. These are all the ways that there can be 70 heads. So you could have 70 chickens, 0 pigs, 70 pigs, 0 chickens, and everything in between. This graph shows all the ways that you can have 200 legs. Between the two, there's only one place where we could have 200 legs and 70 heads, and that's when there's 40 chickens and 30 pigs. So the graph says the exact same thing as my algebra, which says the exact same thing as my table. There is no disputing my argument, nor is there disputing my understanding of the problem and the ability to use math as a tool. Alright, we talked a lot about this in class, the bicycle fly problem. One of the lessons here is that an answer could be right in front of you and you don't know. So many of you decided that they will only be riding for an hour, but then missed that he went 15 miles in an hour, which was his rate of speed, the fly, I mean. But also, we end up with this idea, this notion that a fly is covering a fraction of the distance between the two bikes. If it keeps covering a fraction of the distance over and over, there's actually infinity different turnarounds before it reaches 15 miles. What that means essentially is there is a finite distance, but there's infinite cuttings of that finite distance, and so ultimately the fly will travel 15 kilometers, but it'll take 50 turnarounds to do it. Alright, last one I'm going to talk about on this video, because it's getting a little long, has to do with this problem here. This has to do with intuition in mathematics. Imagining a string wrapping around the earth and then just pushing out an extra inch makes you feel as if there's going to be a whole bunch of extra string required, whereas around a ball, if we push it out an inch, it's not going to require that much. I even told you it requires about 6 1/4 inches more for the ball. As it turns out, though, the relationship between the diameter of a sphere and its circumference is what's called a linear relationship. You guys studied lines last year, and what we know about lines is y equals mx plus b. That's what they told us in the book. But many people in high school do not understand that c equals 2 pi r is a line. It's y equals mx plus b. The c is the y, the slope, m, is 2 pi, and the variable is r. So if we understand that circumference is a linear relationship, then if I add an inch to this ball and get 6 1/4 extra inches of circumference, then I add an inch to this ball, I will also get 6 1/4 extra inches of circumference. Now, this, I'm not going to go over it in the video, is a mathematical argument to prove that it doesn't even matter what the radius is. If I add an inch, it increases my circumference by 2 pi, which is approximately 6.28. So this is an idea to demonstrate how mathematics can be a tool that will help when our intuition fails us. And so here again, a mathematical argument to make that statement. And here's a graph which shows every single inch that I increase will give me 2 pi more circumference. If it's an inch at the beginning or if it's an inch at the end, it's still 6 1/4 inches more strain. The water tank problem we'll talk about, or I talked about in class, just really briefly because I said it's getting long. What this has to do with is rates and how we label our numbers. Numbers have labels, and these labels have meaning. And if we learn to work with labels in doing our mathematics, we're going to understand mathematics at a whole much richer level, and these kinds of tank problems would become incredibly easy. But we have to learn how to do that first. The last one I just added for those students that get done really, really fast. I wanted to put a challenge up there to make sure everybody had a lot of work. But anyway, it turns out that if we unravel the can, we get 5 right triangles, and then we can use the Pythagorean theorem, a squared plus b squared equals c squared, to find out one of those hypotenuses, or hypotenusae, I guess, and then there are 5 of them wrapped around, and therefore there's 150 centimeters of string. So thanks for listening. I hope this was helpful. Have a great day.